So this lesson is about recursive formulas versus explicit formulas. So to start out with, we're given the sequence 100, 50, 25, 12.5, and so on. Write an expression for the nth term of this sequence. Pause the video. When you're finished, start the video back. Hopefully you recognize that this is a geometric sequence with a common ratio of a half. So our expression for finding the nth term would be a sub n equals 100 times 1/2 raised to the n minus 1. This particular formula that you have written is what we call an explicit formula. It is called this because for any given term of the sequence, the explicit expression can be used by substituting the term number in order to determine the term. So go ahead and do the next part. What is the value of the 10th term in this sequence? Pause the video. When you're done, start the video back. All right, so we just substitute 10n for n, and so that gives us 100 times 1/2 raised to the 9th power. And then when we evaluate that, we get that that is 25 over 1.28, which is approximately 0.195. This sequence can also be expressed recursively. The recursive formula basically gives the value of the term in the sequence a sub n based on the previous term a sub n minus 1. To do this, we write an expression for a sub 1 and a sub n. The expression for a sub n will be a function of a sub n minus 1. Wow, okay, so what in the world is that saying? All right, so we're going to write down some steps here for how to write a recursive formula. The very first step in writing a recursive formula is you have to have the first term. And in certain cases, you have to have the first couple of terms. For example, we'll look at the Fibonacci sequence again. In order to write the recursive formula for that one, we have to have the first two terms. But we're going to start out with this one, since this is just a geometric sequence. We have to start by writing the first term. All right, then what we have to do is we have to ask ourselves, what is being done to the first term to get the second term? Well, we know it's being multiplied by 1/2. So then what we do is we use this to write the formula for the next term, a sub n, based on the previous term, which is what we call a sub n minus 1. So it's going to look like this. A sub n is equal to 1/2 times a sub n minus 1. And this is the formula that we use to calculate the next term from its previous term. So I know this is very strange and very weird, but that's what a recursive formula is. It always has two parts. You have to give the first term or the first couple of terms, depending on what the formula is. And then you have to give the formula for how you're going to find the next term using the previous term. So in this case, when I say a sub n minus 1, that means the term before it, I multiply it by 1/2 to get the term I'm at now. And I know this is kind of weird, and hopefully if you need to, pause the video so you can write these steps down. But I'm just going to come over to the side and show you what I mean and how this would work. So if I know that a sub 1 is equal to 100, to get a sub 2, I would half a sub 1. Notice, if n was 2 right here, then 2 minus 1 right here would be 1. So that's why it works. If we make this a sub 2, then a sub n minus 1 would be a sub 1. And so then we use the previous term. Okay, well that's 1/2 times 100, which is 50. And then we would do it again. Okay, to get a sub 3, I'm going to half the previous term, which would have been a sub 2. So that means I'm going to half 50. And half of 50 is 25. But to me, a recursive formula kind of breaks it down. What is the actual pattern? What's actually happening? How are we forming this sequence? So for each of the following sequences, write the explicit and recursive forms. So looking at this first one, hopefully y'all can recognize that this is a geometric sequence because it is multiplying by 2. So the first term is 1 and the common ratio is 2. So therefore, to write the explicit formula, I'm just going to put EF for explicit formula, we just go back to our geometric formula, which is a sub n equals a sub 1 times r to the n minus 1. and we would substitute our values. So we have a sub m is equal to 1 times 2 to the n minus 1. Sometimes you will see that cleaned up and just it'll say a sub n is equal to 2 raised to the n minus 1. All right, but for the recursive formula, this is where we break it down and we really explain the pattern. So remember, it always has to have two parts. The first part is where do you start at? If you don't give the first term, there's no way that anybody could use this formula to calculate the other terms because they wouldn't know where to start at. So in this case, our first term is 1. Sorry, I don't know why I wrote 100 right there. And then to get our next term, we're going to multiply the previous term by 2. So we're going to say 2 times a sub n minus 1 is what would give us a sub n. And that is our recursive formula. All right, so let's look at the next one. This one might be a little bit weird. You might be like, I'm not real sure. But remember, that's obviously not arithmetic. It's not adding the same number or subtracting the same number. If you're not sure what the pattern is and you want to know if it's geometric, just take any term and divide it by its previous term. So if I just come over to the side real quick, and I took, to get r, 2 square root of 3, and divide it by 2, I get that r is the square root of 3. And then if you check that out, it works. 2 times the square root of 3 does give you 2 square root of 3. If you take 2 square root of 3 and multiply it by the square root of 3, that ultimately gives you 2 times 3, which is 6. And so the pattern does continue, and we can see that r is the square root of 3. So again, our first term in this case is 2. Our r value is the square root of 3. So for our explicit formula, since this is geometric, we're going to use that same formula from above, and we would just pop it together. So we would say a sub m is equal to our first term, which is 2, times r raised to the n minus 1. Okay, so for our recursive formula, we would say our first term is 2. To get the next term, we're going to multiply the previous term by the square root of 3. So we'd say that gives us the square root of 3 times a sub n minus 1. Okay, I would like for you to try the next two on your own. Please actually try them. Pause the video, and when you're finished, start the video back. Pause now. So the third problem is also geometric. The first term is 3, and the common ratio is 2. So just going back to what we learned a few days ago, a sub n equals 3 times 2 raised to the n minus 1. The recursive formula would be that the first term is 3, and then a sub n would be 2 times a sub n minus 1. And again, that's just saying to get the next term, multiply 2 by the previous term. The last one is actually arithmetic because it is subtracting 3 each time. So for that one, we have to use our arithmetic formula. And remember, our arithmetic formula is a sub n equals a sub 1 plus n minus 1 times d. I personally, when I'm trying to use the formula, I like to put the d in front. Just it makes it easier to distribute. So our first term is 25. D is negative 3, and so when we set that up, and we clean it up and distribute, and we should get that that is 28 minus 3n. In this case, the recursive formula is going to be a little bit different because we're not multiplying this time, we're subtracting 3. So our first term is 25. To get our next term, so we're going to say to get a sub n, that is equal to the previous term, a sub n minus 1, minus 3. All right, so let's kind of sum this up. We're working with arithmetic sequences. Our explicit formula is the formula that we learned a few days back. But our recursive formula is going to be a sub 1 equals whatever a sub 1 is, whatever that first term is. And then a sub n is equal to a sub n minus 1 plus d. Of course, if d is negative, you'd say minus that d value. All right, for the explicit formula and recursive formula for geometric sequences, so our explicit formula is the one we've been using. And then our recursive formula is going to be that a sub 1 is equal to whatever that first term is, but a sub n will equal r times a sub n minus 1. All right, so that's really neat. That's pretty easy. You can kind of even just study the formulas. But what y'all need to understand is not all recursive forms are arithmetic or geometric. For example, the Fibonacci sequence is a sequence that cannot be written with an explicit formula. It can only be written recursively because it has to have the previous terms to continue to grow. So the way like nautilus shells grow or the beehives are built or pine cones grow, those are all Fibonacci sequences. So that's where we're going to look at some different problems now, and we're going to start using some of our technology. Okay, so before we get into the next problem, where we get into the word problems, we're going to practice using our TI-84s to insert a recursive sequence. And it's kind of a little bit of programming, but once you get used to it, you'll be fine. So looking at this, it says, given the arithmetic sequence 2, 5, 8, and so on, the recursive formula, remember, because this is arithmetic, would be a sub n equals a sub n minus 1 plus d. So in this case, the recursive formula would be a sub n equals a sub n minus 1 plus 3, where a sub 1 equals 2. Recall, a sub n minus 1 represents the previous term. All right, well, here's the deal. In the calculator, it doesn't let you program the subscript notation, so we're going to go back to using functional notation. Well, the first thing we have to do in our calculator is we're going to have to change from function mode to sequence mode. So I'm going to pull it up. Make sure you got your calculators out. What you're going to do is right up here beside your second button, you're going to hit mode. And then once you hit mode, you're going to go down to where you see function, and you're going to scroll over to sequence mode. By the end of this semester, and press enter so that it's stuck there. By the end of the semester, you will actually learn all 4 modes. You'll be able to use function, parametric, polar, and sequence. All right, so then from there, the next step is we're going to go to y equals. Okay, and now we are in sequence mode, and our n min is going to be 1, and that is because we're starting with the first term. So the n min is the value where n starts counting. And guys, if you're looking at your steps on your blue sheet, I am now on step 2. Like I'm literally going down these steps. All right, so then it says enter the recursive formula for u of n. So they call it u of n instead of a sub n. So real quickly, you may want to even write this on your sheet so you know what to do. What you do is when it says u of n, you're going to type u of n minus 1 plus 3. And where that comes from is that our formula is a sub n equals a sub n minus 1 plus 3. But the calculator uses u instead of a, and it uses functional notation instead of subscript notation. So let's go back to our calculator and so you can see what I mean. All right, so where in the world do we get u from? Okay, there's a couple of ways to get it. One, you can press second 7. If you look at your 7, 8, and 9, it's got u, v, and w above it. So if you were trying to program more than one sequence, we're only doing 1 right now, but if we had to program 2, we'd put the next one in the v. All right, and then you're going to hit parenthesis. And guys, when you hit your xt theta n button that you've always clicked for x, it'll now pop up an n because we are in sequence mode. And then say minus 1, close parenthesis, plus 3. And then you come down and it's, in some of y'all's calculators is going to say u of n min because your calculator's older. And just remember, you set n min to be 1. Mine goes ahead and just automatically makes it u of 1. But you should be fine either way. Just kind of go with it. And right there, that's where you're going to put that first term in. And that first term was 2. Going back up here where we had the u at. Sorry. Oops. Another way that you can get u if you have a newer calculator, like one of the, like if you just bought it in the last year or so, is to get u, you can press alpha trace, and look how it pops up different, like it'll pop up u, it pops up u of n minus 1, it pops up some neat stuff there, like yours might just pop up u, v, and w. So some of y'all's calculators will do that and some of y'all's won't, but if it does, it is kind of nice because it makes it a lot easier. All right, so just going back, now that we've got this typed in, we can now go to the table. So we're going to press second graph for our table, and instead of it saying x sub 1, y sub 1, it's now going to have n versus u of n, and it makes that sequence for you, which is really cool with a recursive formula. You can also graph these. To remember, if you're going to graph it, that your calculator is going to show you what you wanted to see. So you may want to go to your window first and set it up. So maybe I want to see the first 10. So I'd say nmin 1, nmax 10, plot start at 1, plot step at 1. But then I'd probably want to fix these down here. So I'm just going to go down to here. My xmin, I'm just going to make -1. That way I can still see my y-axis. But my xmax, I might make 11. That way I can see the first 10 terms of my sequence. And then for my y-min, I might make it -1, but my y-max, you know, it went up much higher than that. Maybe I make it 30. And I don't even know if that'll show us everything, but it'll, you know, at least show us some. And then I'm going to do my y-scale. That's up to you. You could do it by 1 or by 5 or however. And then hit graph. And that's just something you have to play with. And you can see this nice linear pattern because this is an arithmetic sequence, and an arithmetic sequence has a constant rate of change. Okay, so let's look at this application. A lake initially contains 5,200 fish. Each year, the population declines 30% due to fishing and other causes. At the end of each year, the lake is restocked with 400 fish. All right, so folks, we have to think about this. If it is losing 30%, if it declines by 30%, it's keeping 70%. So that's what we're going to use for our multiplier because we want to know how much we have left. So we start out at the beginning of the first year, we have 5,200 fish. All right, to get how many we'd have the next year, we have to take the previous year and multiply it by 0.7. In other words, we're doing 70% of it. So we're going to say 0.7 times a sub n minus 1. But then at the end of each year, it's restocked with 400 fish. So we have to say plus 400. This is pretty neat because this is where this is not arithmetic and it's not geometric. And you would have to use a recursive formula to be able to figure out what happens in the long run or what happens over so many years. And this is what happens in like bank accounts when you're earning interest and making deposits or withdrawals. And that's why they have to use spreadsheets and things like Excel and other types of programs in order to calculate how much money you'll have. All right. So now it says, how many fish are there at the beginning of the 5th year? For this one time, I would really like for us to work this out by hand just so you can see how the process goes. So we already know how many we're going to have after the first year. So the first year is 5,200. So to get the second year, we're going to say 70% of the previous year, because that's what that's saying. So 70% of a sub 1, because this is a sub 2, and we know a sub 1 is 5,200, and then plus 400. And if you pop that into your calculator, we would get that this comes out to be 4,040. So to get a sub 3, we would say 0.7 times a sub 2, which is what we just calculated. This is why you got to use a recursive formula here, because you have to have the year before to be able to calculate the next year. And then we'd say plus 400. So that gives us 3,228. All right, so then to get a sub 4, we would say 0.7 times the previous year, which was 3,228, plus 400, which gives us approximately 2,660. And then finally, to get that 5th year, you're going to do the same process. A sub 5 is equal to 0.7 times the previous year, which we got to be, and you may use the decimal that was in your calculator, or you can use 2,660 plus 400, and it comes out to be approximately 2,262. I'm rounding to a whole number because this is the number of fish, and we can't have a part of a fish. And so at the beginning of the 5th year, we would have 2,262 fish. So, but then the next question says, what happens to the fish population in the lake over time? Well, y'all can see this gets very tedious, and we don't want to sit here and do this by hand all day long. So here's where we'd want to program this into our graphing calculator. All right, so to help you out, I've kind of got it set up. Remember, you go mode sequence, which we should already be there. We're going to click y equals, and this is what we're going to type in, because we have to change it from a sub n minus 1 to u of n minus 1. So you've got this right here. You can look at it, and I want you to try to go ahead and program this in your calculator. Pause the video and get it in your calculator. This is what it should look like once we've programmed this in our calculator. And then what we want to do is go to our table. So we're going to hit second graph for our table. And we just want to start scrolling down to see what happens in the long run. Does this converge, or does this seem to diverge? So you might just start tracing it down, and you can kind of see that over time it starts to look like it's converging to about 1,333 fish. You can keep scrolling down. You can also jump in your table by going to your table setup, which is second window. Sometimes it is kind of slow because it's trying to process it. So if your calculator starts kind of waiting for a second, just give it a minute and let it do its thing. Okay, so since we could see that after we use this recursive formula, in the long run it converged to about 1,333 fish. This is actually where I was talking about the other day. This is what we call a limit, which we will be studying at the end of this semester. So we could say the limit as n approaches infinity of this sequence is 1,333 fish. All right, I would like for y'all to read the next problem, see if you can set up the recursive formula. Pause the video, do it, and then start the video back. Okay, so in this case, guys, it pays an annual interest rate of 3%, and I don't know why that percent is backwards. I'm sorry. Weird. So 3%, but it's compounded monthly. So they're not going to get 3% every month. They're going to get a twelfth of that, so that since there's 12 months in a year. So to figure out the monthly interest, we say 3% divided by 12, which is 0.25%. But of course, we know we have to change that to a decimal, and then because this one's growing, you have to take 100% and then add that percent to it. Some of you may remember these formulas from back when you were in Math 3, like the formula for compound interest is y equals a times 1 plus r over n to the nt. And that's kind of what we're doing right here, is that 1 plus r over n, where r is our interest rate of 0.03, n is 12 months, and then we've got to have that 1 there to hold the original amount because it's growing. All right, so then we're going to program that into our calculators. So if you program it correctly, it should look like this. And it might be a good idea, guys, to write those calculator steps on your notes, because the more you do it, the easier it gets, and you don't have to keep looking it up or looking on the sheet. All right, so let's look at this next question. It says, how much savings will Anna have in her account after 3 years? Well, what you have to remember is that we set this up where n represents the months. We wrote a recursive formula for the savings account balance, a sub n, at the beginning of the nth month. So we're not like using this explicit formula over here. I just was trying to connect to that. This is how much she has each month. So if it has been 3 years, how many months has that been? That's been 36 months. So you have to remember that n is going to be 36. Now, where am I getting this answer? I am not doing this by hand 36 times. I'm using our technology. So I'm going to go right in here to our handy dandy table, and I'm going to look at 36 months, and I can see that when it's been 36 months, she would have, and all you got to do to get the exact amount, guys, is click over on that Y value, look at the bottom of the screen, and you can see that's $4,198.59, round to the nearest hundredths place, because we are talking about money. So then the next question says, how much savings will Anna have in the account after 10 years? Okay, again, we're not going to look for where n is 10 because it's done monthly. So if it's been 10 years, 10 times 12 is 120. That's 120 months. And I surely do not want to scroll all day long, so I'm going to click back into my ends. I'm going to go second window, and I'm going to start this at 120 and press enter. And then I'm going to go back to the table. If it may take a minute Mine went right there. If yours doesn't, don't freak out. Just give it a minute. Let it think. Sometimes it takes a minute for it to calculate. Again, I'm going to click over on that Y value. So that's going to be $14,512.54 when we round. And then it says, how long will it take for Anna to reach a savings of $20,000? Okay, well, we're at $14,000 now. And so you may just kind of keep scrolling, or you might be like, I don't know. Let me just guess. Let's see. Maybe it's going to be 150 months. And go back to your table, see where you're at. If you're not quite there, scroll down, or maybe, jump again. But actually, when I get here, I can look down and see that at 158 months, she has almost $2,000. But when you get to 159 months, she does have that $2,000. So we come over to our paper and make sure we note that on our paper. Answer C was that she had $14,512.54 after 120 months. And then for the last answer, and I'm just going to write on my paper so I know what I did in my table, I could see that at 158 months, she was at $19,938 approximately. And 159 months, she was at $20,088. So with this plan, it would be 159 months. We divide that by 12. That is 13.25 years. So ultimately, that is 13 years and 3 months. And we will be working on these problems together in class because we're going to do some that are not arithmetic and geometric tomorrow. So make sure you've got all this down before then.